This module is an introduction to homeostasis presented by the University of British Columbia and the HIVE. We all like to be comfortable. Since we are able to set the boundaries of our own comfort zone, it's only natural that we feel most comfortable there. Within our comfort zone, we all have our preferences, such as the number of dirty dishes that can be in the sink before we have to clean them, or the amount of laundry that could be in the hamper before we have to do a load. But once the amount of dirty dishes or the amount of laundry gets out of our comfort zone, we start to feel really stressed. And it's that feeling of stress that drives us to do those chores and bring ourselves back to our comfort zone. Well, it turns out that the body also has a bunch of comfort zones that it's trying to maintain. While the front of our brain is responsible for keeping track of our chores, there are other parts of the brain that are responsible for making sure that, among other things, our body temperature, blood pressure, and the amount of food we take in stays within its respective comfort zone. The part of the brain that is most responsible for maintaining those comfort zones is called the hypothalamus, and its role is to maintain those comfort zones. That process of maintaining its comfort zones is called homeostasis. Now, as I've mentioned, homeostasis is the process by which the body maintains its internal environment. The hypothalamus makes sure that temperature, the amount of water that we drink, and the amount of food that we eat stays at an appropriate level, and will make changes if we start to deviate from baseline. If we get too warm, we sweat. If we get too cold, we shiver. If we drink too much water, we will urinate. If we drink too little, we'll retain water. If we eat too much food, we store it as fat. And if we eat too little food, we will break down that fat. All of these processes are ways that the hypothalamus makes sure that our body is working at peak efficiency. But how does the body do this? How does the body and the hypothalamus control all of these comfort zones? Well, it does it through feedback. Let's think about this analogy. You're living with a roommate and you have a common space. But unfortunately, your roommate left a bunch of dirty dishes on the table. Well, what would you do? You're a respectful person and you're a good communicator, so you tell your roommate, hey, I would really appreciate it if we kept the common space clear of dirty dishes. Now, in this scenario, you've got a wonderful roommate, and they take your feedback and happily bring their dishes back to the kitchen. This whole interaction is an example of feedback in our daily lives, and it's exactly how the body maintains many of its comfort zones. In fact, we can break this analogy down and then apply it to the body. Firstly, we'll define our comfort zone as no dirty dishes in the common space. The presence of a dirty dish in the common space disrupts that comfort zone and makes you feel a little stressed. In response to that disruption, you ask your roommate to make sure that the common space is clear of dirty dishes. And as a result, all of the dishes are brought back to the kitchen and the common space no longer has any dirty dishes there. Your comfort zone has now restored and you're no longer stressed. This whole process is called a feedback loop, and it's got some pretty important language that we should define and review. Firstly, we have our comfort zones, which in biology and medicine, we typically refer to those comfort zones as reference ranges. The reference range is basically the normal conditions that the body wants to stay within. Next, we have a disruption that brings us out of the reference range, which we will call a stimulus. Now, a stimulus can be anything that disrupts the body's comfort zone. As has already been discussed a little bit, feedback is an alert to the body that a stimulus has occurred and has resulted in our body being outside of its comfort zone. We have also mentioned a very important part of the brain, the hypothalamus, and it acts as the main control center in homeostasis. The hypothalamus essentially tells the rest of the body how to deal with a stimulus, and that will ultimately bring us back to homeostasis. Lastly, and most importantly, the process that brings us back to the body's comfort zone is referred to as a homeostatic mechanism. Now that we've reviewed some terminology, let's discuss how feedback works. When you go outside and it's warm, what happens? When your body heats up from the sun, you start to sweat and your face becomes really flushed. Essentially, what's happening is your hypothalamus is telling the rest of your body you need to be cooled down. And the most effective way to do that is to sweat and bring blood to the surface of your skin. Now, to reinforce this concept, let's break this analogy down in the exact same way we did with the dirty dishes fiasco. Firstly, the body wants to be around 36.5 degrees Celsius. That's what's considered normal. The warm environment disrupts that comfort zone, which means that the heat from the sun is the stimulus that is disrupting homeostasis. As a result, you sweat and bring blood to the surface of your skin. These are both homeostatic mechanisms that the body uses to cool you down and bring you back to homeostasis. Notice how the body's response to the heat is an attempt to bring our temperature back to baseline, back to 36.5 degrees Celsius. All processes that are trying to bring your body back to baseline are called negative feedback loops. Now, before we go any further, let's just make sure that this is clear. Feedback is an alert to the body that a stimulus has occurred and brought the body out of homeostasis. Negative feedback is a type of feedback that aims to bring the body back to baseline. In this example, we use temperature, but blood pressure, blood pH, blood glucose levels, water balance, they all use negative feedback loops in order to maintain homeostasis. Now, lucky for us, if there is a negative feedback loop, there are also positive feedback loops. But rather than bring the body back to baseline, positive feedback loops are going to bring the body further away from baseline. While that seems a little counterintuitive, positive feedbacks are extremely important. And let's use breastfeeding as an example. We have a hungry baby and a parent that can breastfeed. Now, once the baby is hungry, we will see how a positive feedback loop ensures that the parent gives enough breast milk to satisfy the baby's hunger. When the baby wants to feed, the baby will latch onto the breast and, by suckling, apply pressure to the nipple. The pressure is detected by the parent's body as a stimulus, and the hypothalamus tells the breast to release milk. But as the baby feeds, they're going to continue to suckle and apply more pressure to the parent's nipple. This suckling will then cause more milk to be released, and this in turn will cause even more suckling. Now, this cycle is going to continue until the baby's full, and it's only once the baby's full that they will detach from the breast and the pressure on the nipple will be completely gone, finally returning the parent's body to homeostasis. Now let's quickly break this down in the same way that we did the other examples. Initially, there's no pressure on the parent's nipple, but once the baby's hungry, the baby applies pressure to the nipple via suckling, and that causes milk to be released from the breast. The milk means that the baby applies more pressure, and more pressure means more milk, and this process is only going to end once the baby is full. Now, all positive feedback loops involve a stimulus being amplified over and over and over again until a special event happens. In this case, the baby finishing their meal is the special event that ends the positive feedback loop. Now, these examples of feedback loops, both positive and negative, are great at reacting to a stimulus. However, the body can also predict and mitigate a stimulus before it even happens. This process is called a feed-forward mechanism. In this situation, you enter the kitchen and you've got a wonderful roommate there, and they're going to make you a fresh glass of lemonade with their bare hands. Now, when you see the fresh glass of lemonade, you immediately start to salivate. But how does your body know to salivate just from the sight of lemons and lemonade? Well, it turns out that our brains use many patterns to make our lives easier. In this case, the hypothalamus spoke to the visual processing centers of the brain and said, "Hey, can you just let me know when food's on its way?" And your visual system just happily obliges. What this means is that our brain has made an association that when we see food, we should prepare to digest it. Now, this learned association leads to a feed-forward mechanism that prevents us from leaving our homeostatic comfort zone in the first place. So here's you're inside your comfort zone, your body is happily maintaining homeostasis. Now, the lemonade that your roommate has made is an impending stimulus. The lemonade has the potential to move you out of your comfort zone. So when you see the food, your visual system tells the hypothalamus, hey, food's coming, let's get ready for it. And your hypothalamus starts to take care of it. Your hypothalamus essentially just sends signals that will ultimately result in your salivary glands secreting saliva at the site of the lemonade. Since you started salivating before you even drank the lemonade, you don't leave your comfort zone upon drinking it. The last thing we will do is summarize the concepts that we have just finished discussing. Negative feedback loops maintain homeostasis by bringing the body back to baseline. We used heat as our example, but negative feedbacks are the most common homeostatic mechanism that the body uses. Blood sugar, blood pressure, blood pH, water balance, salt balances, all use negative feedback loops in order to maintain homeostasis. In contrast, positive feedback loops maintain homeostasis by first bringing the body further away from baseline and then waiting until a special event happens. We discussed this concept in terms of breastfeeding, but labor and delivery, clot formation, and even orgasms all use positive feedback mechanisms. Finally, we discussed feed-forward mechanisms, which try to predict and preemptively prevent an incoming stimulus. We primarily see feed-forward mechanisms when preparing to digest food once we see it.